Welcome to the Explainer. Today we're rolling up our sleeves to master the complete operational workflow for building a bare metal ps2 to USB keyboard converter. We're going to use the seriously capable STM32F103C6T6 microcontroller to pull this off. So if you've got an absolutely gorgeous, wonderfully tactile classic keyboard gathering dust because it has an obsolete ps2 connector, or maybe it even has a damaged membrane, well, you're in luck. This explainer is going to show you exactly how to bypass those physical limits and bring that hardware roaring back to life on modern devices. Here's the roadmap for today's workflow. We'll kick things off with resurrecting keyboards, map out the hardware wiring, dig into customizing the layout, do a quick protocol primer, go over flashing the firmware, and finally, plug in and type.
Section 1. Resurrecting keyboards, breathing life into old tech.
So why even take the time to build this? Well, doing it bare metal with the libopenCM3 framework unlocks some absolute killer features. We're talking true plug-and-play USB HID emulation right out of the box, meaning absolutely no messy drivers needed for Windows, macOS, Linux, or even Android. Plus, because we're relying on hardware external interrupts, you get phenomenally low latency. It's essentially zero lag. You also get full 6-key rollover support, meaning you can confidently mash up to 6 keys at once alongside your modifiers, which is a total game changer for fast typing and gaming. And the best part? You get total freedom for custom key remapping directly in the firmware itself.
Section 2. Hardware wiring. Connecting the physical pieces.
All right, let's step out of the theory and tackle the physical hardware. Hooking this up to your STM32 is actually elegantly simple. Your VCC line from the keyboard goes right to the 5V power output on the board to give the keyboard some juice. Ground obviously goes to ground. Now for the communication lines. The PS2 clock line goes directly to pin PA1 and the data line goes to pin PA0. Just make sure both of these are set as inputs with pull-up resistors enabled. That clock line hitting PA1 is super important, by the way, because it's tied directly to the EXTI1 hardware interrupt, which is the secret sauce we'll look at in just a minute.
Now pay close attention to this safety tip because it's a huge lifesaver. If you're used to working with modern microcontrollers, you probably know that sending 5 volts into a 3.3 volt pin usually results in the dreaded magic smoke and a completely fried chip. But here's the genius of using the STM32F103. Pins PA0 and PA1 are specifically 5 volt tolerant. This is a massive win for our operational workflow because it means you get to skip wiring up any messy logic level shifters. You just pipe that 5 volt keyboard logic straight into the board.
Section 3. Customizing layout. Software level translation.
Let's transition over to the software logic. What if that amazing vintage keyboard you found has some damaged membrane traces? Let's say your home row A key is completely shot. If you have dead physical keys, the brilliant hack here is doing a physical swap followed by a software translation. You just pop off a working keycap from somewhere you rarely use, like the F1 key, and physically place it exactly where the dead A key used to be. Pressing that spot now triggers the F1 matrix trace, which is still perfectly functional.
Now, looking at the code, you can see exactly how we translate that physical swap into the right digital output. In your main C file, there is a lookup table. You basically just tell the firmware, hey, when you see the PS2 scan code 0x05, which is F1, do not send F1 to the computer. Instead, output the standard USB HID code 0x04, and boom, the computer perfectly types the letter A. You can see we do the exact same thing to turn F2 into S and F3 into D. You are literally rescuing a broken piece of hardware by rearranging its switches and fixing the mismatch entirely in software. And hey, if your keyboard already works perfectly, you just stick with the standard lookup table we've included.
Section 4. Protocol primer. How the communication works.
Before we actually compile and flash this code, let's take a quick peek under the hood to understand the language our STM32 is translating. The PSR2 protocol is a synchronous serial protocol. It's definitely old school, but it is incredibly reliable. The keyboard itself generates a clock signal, usually oscillating somewhere between 10 and 16 kilohertz. The STM32 doesn't control this pace at all. It just listens. Our firmware uses that EXTI1 interrupt we wired up earlier to grab the data precisely on every single falling edge of that incoming clock signal.
When that data streams in, it arrives in neat little 11-bit chunks. You've got a start bit, which is always a 0 to wake the system up, followed by your 8 data bits containing the scan code sent least significant bit first. Then there's an odd parity bit for a bit of error checking, and finally a stop bit, which is always a 1. The firmware patiently shifts these bits into a register one by one until a full frame is built.
But, things happen in the real world. What if you bump the cable, or there's a tiny electrical glitch, and a bit simply gets dropped? Normally, the system would just sit there waiting forever for a bit that is never going to arrive, causing your whole keyboard to hang. To make the system rock solid, a really clever timeout watchdog is running in the main loop. If it spots that more than 2 milliseconds have ticked by since the very last clock pulse, it assumes the transmission got interrupted. It instantly resets the state machine so the board never loses sync, and you can just keep typing without ever noticing a hiccup.
Section 5. Flashing firmware, the final operational workflow.
All right, we are at the finish line of our operational workflow, compiling your custom code and flashing it onto the microcontroller. We want this end-to-end deployment to be as painless as possible, so the project uses a fantastic modern toolchain. Your first steps are entirely digital. Grab Visual Studio Code, which is totally free, and then install the Platform.io IDE extension from the marketplace. Platform.io is great because it handles all the complicated cross-platform compilation stuff for you, entirely in the background.
Next up, we need a physical way to push that freshly compiled code to the STM32. You'll want to hook up an ST-Link V2 programmer to your board using this exact pinout. 3.3 volts goes to 3.3 volts, ground connects to ground, the SWDIO data line connects to your board's DIO or PA13 pin, and the SWCLK clock line connects to the CLK or PA14 pin. This sets up the direct physical debugging and flashing connection between your computer and the microcontroller.
Time to pull the trigger. Just open the project folder in VS Code, look down at the bottom Platform.io toolbar, and hit the checkmark icon to build the firmware. This is what compiles your C code and any of those custom key maps you might have tweaked. Once you get the success message, click the right arrow icon. That uploads the binary directly through the ST-Link and flashes it permanently onto your board's memory.
Section 6. Plug in and type. Project complete. And that is it. We've done the wiring, sorted the logic, and finished the flashing. Once that upload completes, you can go ahead and disconnect the ST-Link. Your STM32 is now fully configured as a completely standard USB HID keyboard. All you have to do is plug the STM32's USB port into literally any modern laptop, desktop, or even your phone and start typing. This straightforward workflow is all it takes to save incredible vintage hardware from the landfill and give it a fully customized modern interface. It is the perfect marriage of retro mechanics and modern microcomputing. So now that you've got this entire operational workflow down, what vintage keyboard will you resurrect?